Okay, thank you everyone. So it's my pleasure to introduce Wooyoung Choi, who will close our workshop. So for us, Wooyoung.
All right.
Welcome.
So we finally came to the last talk. All right, so this is not really what I wanted to talk about this workshop, but in the last minute, I changed the title to actually, what I was trying to discuss is why you see, shortwave modulation by internal waves and that kind of thing. But the discussion could be quite involved, and it's almost impossible for me to give a reasonable talk to audience who is very tired. I'm tired too, so I have decided not to give a this talk. So, but anyway, if you have any interest, we can discuss that. But instead of addressing this question, I will try to answer to a very simple question. Okay, so hopefully, I don't want to. I hope I don't torture you anymore. Okay, let me start with the KDB equation. So everyone loves it. I do too, but for the sake of today's talk, I would say this equation is not good. Okay, why? What if to derive this equation, we know we have to use two small parameters. One is for long wave, the other is for weakly nonlinear, right? So long wave, as long as I'm interested in long waves, I'm okay. But what if amplitude is no longer small? Can I use KDB theory? Syntactics says no. Your F alpha, that's the measure of nonlinearity, has to be much smaller than 1. What if that is order 1? Is there such a situation? I think so. So for example, if you think of tsunami, right? Then the wave amplitude can be easily 10 meters or 20 meters, you name it. So in that case, no matter what depth you choose, A over H is no longer small. Okay, so we violate the small alpha assumption. Here's another example. Although I'll talk about mostly surface waves, one layer. But previously, we did some lab experiments with the 2 layers. So this is almost the same experiment that you saw in Magda's lab. Okay? The difference is, in Magda's lab, she used, salted water, fresh water, so density is continuous. But at that time, I was lazy. I do not want to mix water with the salt and that kind of thing, right? Also, every time you do the new experiment, you have to set up, stratification again. So for someone like me who is very lazy, use 2 fluids which don't mix each other. Okay, so I can run as many as possible, as long as the interface becomes flat. Okay, so that's what I did. We did some time ago. So in here, you are looking at the silicone oil top above the fresh water. Okay, so in this case, we did almost the same experiments that Magda did, and then we could generate the large amplitude on the interface. Okay? So this is another example of strong nonlinear phenomena. And if you look at the parameter alpha, which is measured by A over H1 or H, in this case, H is the thickness of the top layer, then this easily 1.5 or even higher. Okay? And of course, because this amplitude, the wave is very large, so shear was generated, so we do see carbon sensitivity, okay, more easily than continuous certification. Anyway, so I showed you a couple of examples where you can expect strong nonlinearity. So let's go back to KDB. So I said KDB, I don't like KDB for the sake of talk. And then what do people do? Okay. So this is the equation Nowadays it's called the Serre-Bernard equation. And before, Serre-Bernard, yeah, in between, there's another word by Su and Gardner. And that paper is not so well known. So the people use, Serre-Bernard. But this name is okay because the S stands for Serre. SG stands for Su and Gardner. GN stands for, Green and Nadi. So we cover everyone. So we don't make anyone upset. But to derive this equation using asymptotics, what you have to do is you have to assume beta, which is the long wave parameter, small, but you don't make any assumption on alpha. That's exactly what I want, right? So if you do that, then at the zeroth order approximation is shallow water equation. So no non-dispersive shallow water equations, that's the hyperbolic system, that's what you get. And then if you include, next order term, which is order of beta squared, then you end up with this somewhat ugly term, which physically represents the dispersion. Okay, and if you want to use small amplitude assumption, alpha much less than 1, then you end up with a term over there, uxxt. So that's a business equation. All right. But anyway, so this is we have a low assumption on alpha, so someone can claim that this is model for large amplitude wave. In fact, this weakly nonlinear business equation has been used quite a while in practical applications in coastal engineering, and so that's the model that almost everybody is using. Okay? And nowadays, people try to use this because they saw relatively large amplitude wave events, and so this becomes the standard nowadays. One thing that I want to point out is you want to find the traveling wave solution for any the evolution equation first, right? So if you use a traveling wave answers and so on, then this somewhat ugly dispersive term equations becomes this, okay? Just like a KDV. So cubic nonlinear polynomial or cubic polynomial in zero. So the profile of this equation is exactly such spirit, which is the solution of a KDV, magically. Okay. The only difference is the wave speed is different. And but if you take a small amplitude assumption for A over H, then you recover KDV. But wave profile is exactly the same. In fact, this ODE was found by Rayleigh in 1876. He never claimed that this is for a strongly nonlinear solitary wave. So not many people have realized that the Rayleigh solution is strongly nonlinear solution. People, often think, Rayleigh solution is the KDV, similar to KDV solution, but not quite, because this equation doesn't have any assumption on amplitude. Okay, so, but coastal engineers are not satisfied. We are never satisfied, right, with anything. So they want to increase the order of nonlinearity. Sometimes, the numerical simulation of such model are not, good compared with the field experiments or laboratory experiments. So what do? So they want to increase the order of nonlinear to the next order. Why do we stop? Okay, can I add, something to the order beta to the fourth? Or this is a long wave model, and so if you look at the dispersion relation of this model is good for long waves compared with its parent equations, which is the Euler equations. But if your wavelength is not very, very long compared with the water depth, then this dispersion relation of this long wave model is not good. So what do? They want to use a different variable instead of U bar. U bar here is depth average velocity. Instead of depth average velocity, you pick any vertical level. You use that velocity. Okay, so there is a free parameter going on, and they adjust that free parameter such that the dispersion relation of the model compares well with Euler equation. But whenever they did, they always found the numerical instability. Okay, of course, to avoid that, they put a lot of dissipation and that kind of thing, right? So what I'm going to show from now on is, how I can improve the model, and how can I also improve the numerical, characteristics of the when you solve the average. That's what I'm trying to say. I hope that I gave you enough information why I'm doing this. Right. Oh, so before I did that, of course, people have done this. Water waves has a long history, so somebody should have done something. And so what they did is, okay, they use depth average velocity and add next order terms like that. Of course, by my former advisor, also Roberto's former advisor, did in 1998 and 1999 and so on. So this is a more accurate equation, but if you look at this linear dispersion relation, you have a negative sign here. So for large K, the left-hand side is negative. So in terms of omega is imaginary. Therefore, this problem is unstable for large K. So they improved the equation, but in terms of accuracy, but in terms of the stability, this is a linearly unstable problem. So this one tells you, if you use U bar, depth average velocity, then you cannot really make the system better.
But the exponential growth rate goes to 0 for large K also.
Very good. So it's not really, yeah. But you still have a instability, and the large K has a certain growth rate. Okay. So why we have that? Okay. So we have to go back to linear problem without long wave approximation, and then this is a basically linearized Euler equations in Fourier space. That's what Jacquard did long time ago, along with many other people. and dispersion relation must be this, okay? So here I'm using what? Phi hat, which is the velocity potential at the free surface. So instead of using depth average velocity, you can use the velocity potential as what we normally do for deep water and finite depth. Of course, when we do that, then I have a dispersion relation. But the problem is, we are truncating the full dispersion relation under the assumption of small kh. So when you do that, then you see the first term has a negative. So this is the first order approximation, and this is second order approximation. If you truncate at the first order approximation, then omega squared is negative again. In this case, the growth rate increases with K. So this is the Ilpo's problem. Okay. So even though we often use the velocity potential at the free surface for deep and finite depth problems, for long waves, you shouldn't use it. Unless you use the even order approximation. First order is Ilpo's, second order is Ilpo's, earphones and earphones and so on. Okay. Of course, once you do that, you don't have to, use, once you know this, you don't have to use, that surface velocity or velocity potential. Then, can you use depth average velocity? Similar thing happens. In this case, odd number is stable and even number makes the system unstable.
But then you use the rational approximation, but then.
Yeah, so that's what people do, right? But if I want to avoid any of this, what should I do? I have to choose, the velocity potential at the bottom. If I do that, then when I truncate at any order, I always have positive terms. So at least, the problem is linearly opposed. Okay?
Level like the property.
No. So you have to be at the bottom. You cannot be in the middle, okay?
Is it the only level that satisfies?
Oh, yeah, that's what inside of a water. Okay. So I like this, bottom velocity potential because it's a linear, anything linearly workable. So once I know which variable I use, I derive the equation. I don't want to bother you how to do it. Just if you believe me, I can derive the long-wave model at any order of approximation. It's infinite series. Okay, explicit series. So I just give you the second order model. Still ugly, but I'm not going to solve it. Somebody else will solve it numerically, so it's okay, I guess. But anyway, so this is the blue lines that the second order terms, and this is the next order term. A first order term and second order terms and so on. And as I said, the dispersion relation gives, always real frequency. All right. So I was happy. When did I start?
Finish it, so if you could run like 35 minutes. 10 more minutes.
10 more minutes. Okay. So now I have a evolution equation written in infinite series. So this is equivalent to Euler equations. Of course, I'm not going to use infinite number of terms, right? If I need to use infinite number of terms, then it's better to use Euler equations. But I'm going to trust it. But at this point, I want to find solitary wave solutions of this infinite series, the evolution equation of infinite series. We can do that. So if you read me, at the leading order, I have OD that I showed you before. So that's a Rayleigh solution. I can keep doing it. Normally I wouldn't do it, but I was on sabbatical in Korea. Not many people bothered me, so I could, doing this using Mathematica. But this is the third order solution. So I corrected Rayleigh solution to the third order. Remember, in 60s, 70s, we obtained, the series solutions, right? For solitary waves under the assumption of weakly nonlinear. So under the weakly nonlinear assumption. Here, this solution is, the solution without that assumption. So if I impose, weakly nonlinear assumption here, then I'll recover all the solutions that people have found previously. Okay. How good is it? Okay, so I'm comparing the first, second, third order approximations with the Euler equations. As you can see, the symbols efficiency in Euler solutions. So as I increase the order of the nonlinearity, solution gets better and better. And this is the vertical structure velocity, horizontal velocity in Z. And as you can see, third order solution is on top of the Euler solution. Okay. So which means the syntax that I carried on is not, is not bad. So,
And weekly it's evening.
weekly nonlinear is, must be KDB. Okay, so it'll be KDB actually. Okay, so, thanks. So that's why I don't like, KDB theory. All right. So, this kind of idea seems to be working. But if you want to solve this problem using finite difference approximation, and then because you have a high order derivative, right? So it's the steep problem numerically. So if you don't handle the high order derivative term correctly, then you would be in trouble. So people often use in practice, people often use finite central difference. And if you do that, then basically what you're solving is not exactly what I drive. Yeah. So as you can see, there are many terms which are proportional to delta x squared, which shouldn't be there, but it's there because of truncation errors. Okay. And because of that, it's, I obtained, beautiful dispersion relation, but, the modified equation that I really solve it numerically completely mess up, dispersion relation. This one tells me I have to approximate derivative very accurately to solve this type of equation. So I need a spectral accuracy, so I use, the pseudo-spectral method and so on. Once I do that, then I can solve, the equations, very stably. So I put second order, so it's a wave and let it go, and then you see that. You're wondering why you have a, waves traveling this way. The reason is this is a second order solution of Euler equations, not the exact solution of second order system. Okay, so there is some adjustment period, and then after that it's good. Okay, and we also checked, the performance of this the numerical solution for unsteady problem, simple problem, for a head-on collision, and using experiment of Chen and Yang. And as you can see, symbols are the experiment this time, and the solid lines are the second order solution, regularized. And if you can see, Serre-Grignani equations or first order regularized equations, don't give good solution compared with the experiments. So this is a justification, my justification of why you have to include high order nonlinearity for large amplitude waves. In this case, the amplitude is not small at all. Okay. So I hope, I gave you enough, the reason why I'm doing that. In addition to I was on sabbatical, so I could do this. All right, so I made. Yeah. So I extend that to quantum topography, internal waves, and so on, but I'll skip that. And finally, this is what I discussed. And if you want to know some details, these are some papers that I wrote about this. And this is just in case that you don't have time to go to ocean, or you don't have a lab, you can do the, so it upstream, propagating circular waves can be generated when your city is flooded. So all you have to do is bring truck or car. You move with a critical speed, which is square root of g times h. So g is 9.81, h in meters, and pick the product and then square root, and then you move. And then when your car speed is close to critical speed, then you can generate circular waves like this. Okay. By the way, this is in Korea, so that's where I came from. All right. Thank you.
Okay, thanks, Will. questions, please. Yeah.
So, this part with that we need to use what looks absolutely beautiful, but is there still some downside in that? You know, is there some limitation when you increase amplitude?
Okay, so why you use, depth average velocity for the long wave model, the long wave modeling is, the conservation of mass. You can have exact conservation of mass if you use, depth average velocity. So in this case, we don't have the exact conservation of mass, and also you bring, high order derivatives and so on. But as I showed you, we can overcome that in different ways. So, yeah.
Okay.
Yeah.
This, your equation, I mean, when you, what the velocity, it means energy conservation law.
Okay, so this is not exact Hamiltonian system. Okay? So I don't have a exact conservation of energy. So that's why you see the dual decay here. And but the one thing, no, actually, sorry. Decay is there, but the decay is a high order, so it's very small. Okay? And the decay of energy that I showed you over there is, due to shed of linear waves for the adjustment period.
Same decay is there.
Yeah, it doesn't conserve energy.
Conservation of energy.
It's not conserved. Let me put it that way.
Maybe
It conserves asymptotically. How about that?
Yeah, really. It's more like a comment.
Okay.
The three talks in this session were only nonlinear models, and it kind of makes an impression that ADV and generally between nonlinear is not working. This is correct to some extent when we speak about these rate amplitudes, but there is a kind of way to extend between nonlinear modeling KDB type models similar to how this equation, for example, extends the range of validity to be shown. Right? So there is the extended KDB equation, not just Gardner, but extended, which includes all the terms appearing at the next order. And as we have recently shown, for example, within the scope of 2D Business modeling, this significantly extends the range of validity of the Bitcoin nonlinear. And we went all the way up to epsilon equal to 0.5. So waves which have the amplitude equal to half of the depth of the fluid, and linear nonlinear modeling was on top of full numerical simulation for even for two-dimensional models. So, and then this naturally extends all the results that we have in integral systems with the help of program and focus on type the identity transformations, for example, to the level of the extended models, and there is a scope for a lot of analytical dimensions in analytical, which can extend the nonlinear model to the base of at least moderate amplitude modulation.
Okay, carry on.
Yeah.
As I said, I don't like, KDB for the sake of today's now. I like it. Okay? I like KDB, I extend KDB, and without that, we don't have any understanding. So don't take, what I said in the wrong way. So yeah, in some set, cases, usually nonlinear theory is good enough, and we don't have to use such a thing. But in practice, people don't use, in practice means in real, program, the people working on coastal area or ocean area, right? They don't use, KDB or anything. They use something like this. So that's the, target that I was trying to.
I have
talk
all
to.
the line for her, but you never like to
Okay.
Okay, let's start Wooyoung and all of us.